So today's tutorial has three problems and we have to also discuss the quiz problems. I hope you guys have all tried this one. So this tutorial is all about actually virtual work, okay? So first problem, if you see a cart of mass M is connected to a despot with constant B. So this card is actually connected to this. So a force Ft on the mass, Ft is acting on this mass, and this force is also given to us. And you see this force is actually time dependent force. So it's not conservative force. And we have to write the Lagrangian equation and derive the equation of motion. Then after long time after long time, what will happen to the motion that we have to find? So for that, what you do is you first see what are the forces acting on this. But one force is along this one is time dependent force, and another one is because of this despot, which will give a drag force. Okay, drag force will be of this type, Bx dot type. Okay, it will basically reduce the velocity. So now both these forces are non-conservative forces. So what you do first is you first write the Lagrangian considering only the conservative forces. Oh, before that, what is the degree of freedom of this problem? Anybody?
One.
One, because it's only allowed to move in x direction. So we will be considering x as generalized coordinate. So let us write the potential. What will be the potential? No spring, no gravity is also fixed. So this will be zero only, some constant. Now let us write the kinetic energy. So kinetic energy will be half m x dot square. Okay, I will be writing m oblique m for that. So this is the kinetic energy. So what will be the Lagrangian? Lagrangian will be simply half m x dot square. We have still not incorporated this ft and bx dot. So our equation will be ddt of dl by dq dot minus dl by dq in absence of any non-conservative forces. This is equal to zero, right? You guys remember this equation?
Yes, we do.
Okay. So if you have some non-conservative forces, we have to also take them into account. So we take them into account by using some generalized force, right? This is called some capital QG. Okay. And this generalized force, we can find it. This we have done in the class. So the QJ is actually written as sum over all the particles Fi dot delta Ri by delta Qj. This is how we find the generalized force. Okay, and where it is actually related to, it is related to the virtual work done. Virtual work done is actually defined as sum over order particles Fi. You have to remember all these things. Okay, Fi dot delta Ri, virtual displacement. This can be actually simplified to generalized coordinates, generalized forces like this Qg delta Qg. So if you now compare this part and this part, you can find Qg will be equal to this. Okay. Now for our question, our Ri, our any position vector of this card can be written as Ri equal to simply x cap. So dri by our dqg will be simply equal to d dx x cap divided by dx, because our generalized coordinate is x. Are you guys with me?
Yes, we
Yes.
do.
Okay. If you get any confusion, just stop me and ask me. Okay. Okay. Now this part is simple. So we are getting there. Dri by del qj is nothing but x cap. So once you know this, your qj is simple now. So what are the generalized forces acting on that? One is Ft f of t, which is acting along x cap plus x cap, dot our del ri by del qj, which is nothing but x cap again. Okay, plus another force, this one b x dot, which is acting along.
Excuse me, भैया
हाँ बोलो.
भैया this generalized force only comes for non-conservative forces, right?
No, it generalized force comes for all the forces. Okay, if you write your equation like
Okay.
this, then you have to consider the generalized forces due to the non-conservative forces. But
Non-conservative.
if you
Okay.
want to write for all the forces, you have to write your equation like this. This L has to be replaced by your total kinetic energy. Okay,
Okay. Okay.
so dt is equal to qj. This is actually for all
Okay. Okay.
forces. Now, if you separate these all forces in terms of one conservative forces and one
Mm-hmm.
non-conservative forces, then this conservative force will go this way and this will give some potential and it will be included in the Lagrangian. Okay, only the
Yeah.
non-conservative portions will remain here.
Okay. Thank you.
Okay, we were here. So ftx dot, this part is done. Now another force is px dot, which is acting along minus x cap. So again, dot del ri by del qj. We are using this definition. So finally, we got that our generalized force is nothing but our simple Ft minus Bx term. That's it. You just have to know this this formalism, how to find your generalized forces. This part is done. Once you know this, you are simply, you have already done this in quiz, also in rest of the tutorials as well. So ddt or dl by dx dot. dl by dx dot is nothing but mx dot. So ddt of mx dot minus dl by dq. No q, no x term is there, so this part will be 0 simply, equal to. Now we have to write qj. Qj is nothing but our ft. Ft we know that in the question it is given as this. Then that's it. Are you guys with me?
Yes, we.
So this is the equation of motion which we are getting. Derive the equation of motion. So this is our equation of motion. The thing is, if you will not know, I think you don't know how to solve this equation. You will get this in MA courses in second semester. Okay. This is called second order differential equation because double dot derivative here. Then this is an inhomogeneous but second order inhomogeneous ordinary differential equation. So once you solve it, without solving also you can solve this. Without solving this equation also you can finish this question. Okay, so let us finish this first. It's saying that after long time, what kind of motion this mass will exhibit. So after long time, this system will go to steady state. Okay, so in steady state your velocity will become constant. Sorry, your velocity will become zero. So this equation will reduce to, in steady state, this equation will reduce to simple like this. Now you know how to solve this equation, right? This is mx double dot is equal to some cos omega t. So our x will be equal to some constant cos omega t plus phi. So if you, we have already solved this part. Okay, this is for when this oscillation is not there. Initial force is f not equal to 0. So final solution of this equation will look like actually this: a plus b e to the power minus d by m times of t plus some c cos omega t plus phi. So that's why your solution actually will look like this. It will have an exponential decay. Over the top, it will have some oscillation. And this oscillation after very long time t will remain like this. This part is actually our steady state. So the next problem. So next problem, there is a pole. This pole is actually tilted, okay? Then we are tying this pole with the help of a rope. And you will see this tension will be generated along this rope, and because of this weight, the post will be like this. So we have to, under these circumstances, using the method of virtual work, find the tension in the rope. So we have to find the tension. So first of all, using virtual work. So we know our virtual work done will be written like this: Fi delta dot delta Ri. Okay. So that means you have to know your Ri, and the Fi you already know. So let us write Ri first. Ri is nothing but, suppose this 3 meter length, na? Let me consider L to be equal to 3 meter. So L cos theta x cap plus L sin theta. This will be minus phi cap. This part is fine. I want to write the position of this point from origin. Okay. So we need actually delta Ri. So this is simple. L sin
Yeah, why
theta.
will it be minus y cap?
Y we will be
It will be a minus y cap. Why will it be minus y cap?
L sin. Oh, sorry. Yeah, L sin theta plus y cap. Yes. Thank you. L cos theta delta theta minus y cap. So, sorry. This one will be minus, and this one will be L cos theta delta theta plus y cap. This part is fine. I think this is fine.
Yep.
Yeah. So let us write the forces also now. So what is the force acting at this point? One is W, which is pointing along minus phi cap, and another one is tension. But tension is actually along different lines. So let us find the angle. What is this angle? So this angle is theta. This angle is alpha. That means this angle must be alpha minus theta, right?
Yes, yes, yes.
Theta minus alpha or alpha minus theta?
Theta,
This is 180
theta
minus
minus alpha. Theta
theta
minus
minus
alpha.
alpha. Yes.
Because theta is on the outside. Out,
Yeah.
it is the
These two
exterior
angles should
angle.
be added. So this will be theta minus alpha. Now you know that this angle is theta
Yeah,
minus alpha. हाँ बोलो.
With theta
yeah,
only,
the
na?
angle rope makes is alpha and the pole makes is
Okay. Wait. So this is theta. This is alpha. So we are supposed to find this angle. This will be simply how much?
Theta minus alpha.
So this is done. So once you know this angle, we have to write the component of t along this direction and this direction. This is alpha. This is also alpha. So this will be t cos alpha along minus x square plus t sin alpha along minus y cube. Is it correct? I want to write the force.
Okay.
This is fine, right? Our t is like this. We want to take the x and y component of this t. This is
Yes.
okay. So once you write this, your delta w will be simply this dot with this. So w plus T sine alpha dotted with, there is a minus sign also, with y cap. Y cap is L cos theta delta theta. Plus T cos alpha with a minus sign dotted with this, which is minus of L sine theta delta theta. Okay. So we got that our delta W will be equal to minus of W plus, okay, let us note it. So this, the delta W will be equal to 0 because this is a virtual word. So we can write it equal to 0. Now if you simplify it, you will get that minus of W plus T sine alpha L cos theta is equal to minus of T cos alpha L sin theta. Right? We will simplify this and we will get this. Now from here you can find T. T will be equal to L will get cancelled. W cos theta divided by sin alpha cos theta minus cos alpha sin theta, which is nothing but W cos theta divided by sin of alpha minus theta. Are you guys with me?
Yeah, probably there's a sign mistake.
कहाँ पे?
Uh, Last step only. Oh,
W
Yes, भैया, that will be positive ना? अच्छा नहीं.
minus of the cos cos alpha term will be positive, na bhaiya?
cos alpha term will be positive. Yes, 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 yes. Mhm. Now it's fine, I think.
Yes, we have.
The third problem. Third problem is also similar. You first have, here you have two generalized coordinates actually, theta 1 and theta 2 both. So first you write the what are the forces acting on this. This will be m1g along this. Here will be m2g along this. So you know all the forces, but force acting on particle 1 you can write. Force acting on particle 2 you can write. Then you have to write what is R1. What is R1? You will find R1 will be in terms of theta 1 and theta 2 you write. So position of this one particle, which will be L1 sine theta 1 x cap and L1 sine theta L1 cos theta 1 minus y cap. You can write R1 and R2. Once you write R1 and R2, then you again apply the virtual work principle. Virtual work will be equal to sum over all the external forces dot delta Ri. You know your Ri's. You can take the this virtual displacement. Now here we are neglecting the virtual work done by the tension forces. Why? Because it's an internal force. The sum of all the virtual works done by the internal forces equal to 0. This thing we are applying here, so you will be remaining only with M1G, M2G and capital F. Okay, so let us write the virtual work done by this. So first one is F1 dot delta R1. Then another one is F2 dot delta R2. These are the two forces acting. So that's why we will be writing like this. In particle 1, for the particle 1, our M1G is acting along minus y cap. And delta R1, if you write R1 here, we will get that R1 is equal to L1 cos theta 1 minus y cap plus L1 sin theta 1 plus x cap. So delta R1 will be equal to minus of L sin theta 1 delta theta 1 minus of y cap, which will give us plus y cap plus this will give something which will be along x cap, but because of this dot product this term will give 0 plus f2. Similarly, if we write for f2, our f2 is minus m2g y cap plus f x cap dot here. Now our R2 will be actually a little bit complicated. It will have this position plus this position. So that's why our R2 will be equal to L2 sin theta 2 plus L1 sin theta 1 x cap plus L2 cos theta 2 plus L1 cos theta 1 y cap. Okay. So you find what will be delta R2 from this. You can find, you write here, you take the dot product, then your final equation will be of this type, delta theta 1 plus something into delta theta 2. And you know that this virtual work done will be equal to 0. Now you see your theta 1 and theta 2 are independent coordinates. They are generalized coordinates. So that's why you can make this thing equal to 0 and make this thing equal to 0, and you will get two equations from this. From there, you can find what will be your theta 1, theta 1 and theta 2, at which this thing will be in equilibrium. Can you do it by yourself? Because we are running out of time, so that's why I don't feel like doing it.
Yes, we have done it. I done.
Similarly, if you see all the three approaches you try, you can also do the same thing using, because your delta W can also be written like this, delta Qj, del Qj. So you will be having two. One will be Q theta 1, delta theta 1, plus another will be Q theta 2, delta theta 2. Now you know that these are in terms of generalized coordinates. So that's why you can simply write Q theta 1 equal to 0 and Q theta 2 equal to 0. You cannot write from here F1 equal to 0 and F2 equal to 0, okay? Because they are not in terms of your generalized coordinates. But once you convert it to in terms of your generalized coordinate, you can separately write your Q theta 1, Q theta 2 be equal to 0. You try this approach also, you will get the same thing.